Binomial distributions. A Bernoulli trial is a random experiment with the following features. The outcome can be classified as either a success or a failure. Those are the only two options, and each is mutually exclusive. The probability of success is P, and the probability of failure is Q, which is the complement of P, or 1 minus P. A Bernoulli random variable is a variable assigned to represent the successes in a Bernoulli trial. If we wish to keep track of the number of successes that occur in repeated Bernoulli trials, we use what is called a binomial random variable. A binomial experiment occurs when the following conditions are met. Each trial can result in only one of two mutually exclusive outcomes, which are success or failure. There are a fixed number of trials. Outcomes of different trials are independent. And the probability that a trial results in success is the same for all trials. The random variable x, set to represent the number of successes in a binomial experiment, is a binomial distribution with parameters p and n, where p represents the probability of success and n is the number of trials. The possible values of x are whole numbers that range from 0 to n, and as abbreviation, we use this notation to state that x is a binomial random variable. Binomial probabilities are calculated using this formula. This formula includes the formula for combinations. The probability that x is equal to a particular value k, in other words, we have k successes exactly, is the combination of n choose k times p to the k times 1 minus p to the n minus k. If you're using RStudio or the TI-83 or 84 calculators, here are the commands. I've listed the commands for the probability that x is equal to a certain number of trials, less than or equal to a certain number of trials, or greater than a certain number of trials. Remember, less than or equal to does not mean the same as less than. These are discrete distributions and we can equal certain values. So with and without that symbol makes a difference. The mean and variance of a binomial distribution are computed using the following formulas. The mean is equal to the number of trials times the probability of success. The variance is equal to the number of trials times the probability of success times the probability of failure. Example: a fair coin is flipped 30 times. The 30 represents our number of trials, so we have a fixed number of trials. Each time we flip the coin, our result is not dependent on the previous result, so each trial is mutually exclusive. The probability of success for each coin flip will be 1/2. In these examples, we're looking for heads, so we'll consider our probability of success to be getting a heads when we flip the coin. What's the probability that the coin comes up heads exactly 12 times? According to our formula, we will do 30, our n, c, 12, our k, times the probability of success to the k and the probability of failure to the n minus k. Now, using the graphing calculator or RStudio, So we're going to use the calculator to compute the probability that x is 12 in this binomial experiment. So we're going to do second distribution, or variables, and we can scroll very far down or we can scroll up. It's basically at the bottom of the list. And we're going to use the command binom PDF. Need to go up one more. For an equals, and when we have inequalities, we use the CDF, the cumulative distribution. So I'm going to do binom PDF. I'm going to hit enter. We have 30 trials. Our probability of success is 0.5, and we want to figure out the probability of having exactly 12 successes. If you have a TI-83 or an 84 that's not a plus C silver, then you would just enter like this: N, then the P, then your K, your number of successes you want. And our answer is 0.080553093. Now part B, we want to know what's the probability that the coin comes up with heads strictly less than 12 times. Well, our command for the TI and for our studio when we're working with less than is a less than or equals to. So if I want to write this with a less than or equals to, we have to think about what's going on here. Less than 12, well, the first value, because these take on whole number values 0 through n, the next number less than 12 is 11, and we would be including 11. So this probability is the same as the probability of x being less than or equal to 11. So in our calculator, if we had to do this by hand with the formula, we would add up the probability that x is 0, 1, 2, 3, all the way to 11. It'd be quite time consuming, so it's nice to have technology. Okay, so for the less than, I'm going to hit second distribution. Again, I'm going to scroll up instead of down. We have the less than or equal to, so that's binom CDF. 30 trials. Probability of success is 0.5, and we're doing less than or equal to 11. .1002. There's that. Okay, what is the probability that the coin comes up with heads more than 12 times? And this is more than but not equal to, strictly greater than. Well, greater than 12 is the same thing as the complement of less than or equal to 12, and that's why we will use 1 minus binomial CDF of 30.512 on the calculator. This comes out to be 0.8192. The expected number of heads, our expected value for a binomial is found by n times p. So for this problem we will do 30 times 1/2. So we would expect to have 15 heads. Another example. Suppose it's known that 80% of the people exposed to the flu virus contract the flu. Out of a family of 5 exposed to the virus, what's the probability that no one will contract the flu, all will contract the flu, exactly 2, or at least 2 will get the flu? So we're asking about getting the flu. So it's obviously our success if we get the flu. So our probability of success is 0.8. Our family has 5 people. That's how many trials we'll have. So the probability that no one gets the flu would be the probability that x is equal to 0. That'll be 5c0, 0.8, our success to the 0, and 1 minus 0.8 to the 5 minus 0. If I'm doing this on the calculator, then I'm going to use binomial or binom PDF, and it would be 5.8 and 0 would be what I'd enter. And this answer is 0.00032. Now the probability that all will contract the flu would be the probability that x is 5. Again, if I use the formula, this would be 5c5, 0.8 to the 5, and 1 minus 0.8 to the 5 minus 5. Or I can use the binomial PDF command with 5, 0.8, 5. Our answer will be 0.3277. The probability that exactly 2 people will get the flu will be 5c2, 0.8 to the second, 1 minus 0.8 to the 5 minus 2. Or again, we can use the binomial PDF command, or if we're in RStudio, our command is dbinom. This answer will be 0.0512. At least 2 getting the flu would be 2 or more, so greater than or including 2. Now again, with our formulas, if we're going to be plugging into the calculator RStudio, this does need to be a less than or equal to. So I can think about, I can have 0 people, 1 people, 2 people, 3 people, 4 people, or 5 people getting the flu. Greater than or equal to consists of 2, 3, 4, or 5. That's the complement of 1 or 0. So this is the same thing as 1 minus the probability that x is less than or equal to 1. So using the calculator, we do 1 minus binomial CDF, this time because it's an inequality, 5.8 and 1. Using RStudio, our command would be 1 minus p binom, and we put our k first here, then our n, then our p. Either way, this would be 0.9933. Continuing this problem, letting x equal the number of family members contracting the flu, if I want to create a probability distribution table, it would look like this. So we have our random variable x, and we have the probability that x is equal to our values 0, 1, 2, 3, 4, or our maximum 5. That was our n. So as we found earlier, the probability that x is 0 is 0.00032. Using the same procedure, the probability that x is 1 will be 0.0064. The probability that x is equal to 2 is 0.0512. The probability that exactly 3 contract the flu is 0.2048. The probability of 4 getting the flu is 0.4096. And again, as we saw in example 2, the probability that exactly 5 people get the flu is 0.32768. So our mean or expected value for this distribution would be 0 times 0.00032 plus 1 times 0.0064 plus 2 times 0.0512 plus 3 times 0.2048 plus 4 times 0.4096 plus 5 times 0.32768. And this answer is exactly what we expect, which is the same as n times p, or 5 times 0.8, which is 4. Our variance is n times p times 1 minus p. So 5 times 0.8 times 1 minus 0.8, which is 0.2, which gives us a variance of 0.8. Now if I wanted the standard deviation, I would square root this.